So we've taken somewhat of an extensive look about DNA structure and DNA purpose and how that relates to RNA, which then how that relates to protein production. And in that discussion, we talked about using heat to separate the DNA strands from each other in the laboratory. And we can use heat to separate and glue these things together from each other. And then if we just cool it back down, we didn't mention that during the time, but if we just cool that back down, you're actually going to see DNA does a pretty good job assembling itself back together without no help from you. It's made to do that because, again, it's made to separate and it's made to come back together and reform the way that it was made in the beginning. So we call this process renature. So if I heat DNA up and denature it, that means I'm separating the strands together. If I cool the DNA back down slowly, the DNA kind of finds where it needs to go and it figures out the right orientation that it needs to be in, and then it begins to glue itself back together. And this gluing back together is what we call renature. So denature DNA means to rip apart, and renature DNA basically means allow it to come back together and be glued back together now. So we can simply do that just by cooling the temperature down below the melting temperature. And we talked about the purpose and how to analyze for that. Typically, rule of thumb is that you want to go 25 degrees or below. And that process can be called renature, or that process can also be called anneal, A-N-N-E-A-L. The annealing process can go on. It kind of means to heal itself. Little DNA has been ripped apart and now it needs to heal itself like Wolverine does. So that's the annealing process. Now we can take advantage of this in the laboratory. If we understand that we can separate DNA, and then if we can replicate that DNA in the laboratory instead of inside of your body, and then if we can take that DNA and anneal itself and allow it to kind of go back to where it came from, then we could start replicating DNA outside of the body and inside of a test tube. And that's exactly what we do with the process called polymerase chain reaction. So polymerase chain reaction is this laboratory method that will take DNA and replicate DNA in an automated fashion. So polymerase chain reaction is abbreviated as PCR. So if you ever find a job advertisement or if you ever see a method that uses PCR, that's exactly what that means. Polymerase chain reaction. So what we do in PCR is that we have this DNA strand, and here's the DNA strand that we want to amplify or that we want to replicate. And we heat this DNA strand up. 95 degrees Celsius is what we do. So 95 degrees Celsius, this DNA strand separates into two. So water boils at 100. So this is a little bit lower than the boiling point of water. So DNA strand will separate into the two strands. And then what we do is that we cool it down a little bit. 54 degrees Celsius is what we go. And then we attach what we call these primers on. So the primers basically are kind of an anchor point. These primers are going onto the DNA. It's latching onto the DNA to create a starting point for us. And we cool it down for that reason because we need it to cool down and to settle down for those primers to latch on. Once the primers latch on, we then heat the DNA back up to 72 degrees Celsius. And by heating it back up, what we are doing is that we are kind of helping this replication process along. We're giving it a nice jacuzzi, we're giving it a little bit of temperature, a little bit of warm water to go through, or warm solvent, to go through and begin to replicate the strand. And that's what you're seeing here. So the primer has went on, that's this red piece, and at 72 degrees Celsius, now the replication process has begun. And we're seeing that this strand has been replicated now. The same thing's happening over here. The primer has went on, and once the primer goes on, then the base pairs begin to get attached and this DNA strand begins to replicate itself. So at 72 degrees, we are seeing that the DNA is getting made. So this is a polymerase that basically has started to replicate itself. And then we repeat that whole process over and over and over and over. So we start with one DNA strand, we end up with two. We then have two DNA strands, and then each of those get replicated, and we end up with four. We then have four of those DNA strands. We replicate each one of those four, and now we get, well, four, two, and two, and two, and two. That leaves me with eight, right? And then we replicate all eight of those, and then we continue on and on and on and on and on. So you can see how this begins to get multiplied and amplified, which is why we call it amplification. So this is a way that I could maybe go to a crime scene and get maybe a swab of blood, or maybe swab your cheek and have a DNA sample brought into the lab. And if it's not enough for me to work with, because it probably isn't, what will happen is that I can then take that DNA sample and put it into a PCR instrument, and this PCR instrument will heat and cool, heat and cool, heat and cool with all of these primers and base pairs in them, and it will begin to amplify the DNA, so that way I have more to work with. So, very good way in forensics, especially, for me to take a DNA sample, replicate it, multiply it out, get me enough to work with so I can do some testing on it, and then go from that point on. So, PCR, that is what that stands for, polymerase chain reaction. Uh, 20 cycles is about the 20 to 30 cycles is about the common routine for a PCR instrument. This increases the amount 1,000,000 fold. So you can easily see how we amplify very quickly DNA when we need it. A lot of times these are automated processes. We start them the morning of, and they're typically finished that evening, or we start them the evening and let them run overnight, and then by the next morning they're perfectly done. So again, forensics uses it drastically for this reason. It gives me a DNA sample. I can extract the DNA from that very small sample. I can amplify that and create more and more and more and more of that DNA in a laboratory, and that way I can do some of these other testing that I need to do on the actual instrument itself, or the DNA itself. This is a PCR instrument. Over here are just keyboards for settings and user entry, and then this tells you basically what's going on as far as the program goes. This piece up here at the top lifts up, and there's actually a well on the inside of there that takes centrifuge tubes, or microcentrifuge tubes, or PCR tubes if you're being very specific, and these PCR tubes will have your DNA in them that you want to be amplified. So in the tubes they go, you close the lid. This is kind of the oven that goes on. This is where the samples get heated up and cooled down. Here's another view of another PCR instrument. Same kind of thing, user entry port here, display readout here. This is the PCR well, where you would put your plastic tubes filled with your DNA in, and you sit them down on top of this instrument and you close it down. So this is again another view of a PCR Pcr instrument. Here's another one. This is just a PCR well that doesn't really get removed that easily, and you can kind of see them putting the microcentrifuge tubes in the top here. This opens up, and when they get ready to run it, they'll close this back down and they'll hit the start button, and they'll come back a little bit later on. This must be a private Japanese school because you see them all in the same kind of outfits, and you see them in the little Sailor Moon bow ties and the Sailor Moon skirts. Okay, that's the story with PCR and the purpose of PCR, at least, polymerase chain reaction. And again, PCR is a method that's commonly done in a biotechnology laboratory especially, but it requires a little bit of heat, it requires a little bit of cooling down, it requires a little bit of primer, and it also requires some base pair mixes. So we need to put the A, T, G's, and C's in there so that way it can start to replicate itself like it should. So that's the purpose of PCR. When you look at it in a job ad, don't be surprised. You might be lucky enough to do it this semester if you make it that far. If so, then good news for you. That just puts you ahead of the competition. So, with that said, that's it of the lecture. We don't really have to go any more into the lecture after this point. We've talked about everything there is to know about DNA, RNA, and protein world. So that also finishes up the lectures for the course. So if you're watching this video, there's no more videos for you to watch. Aren't you excited? So now you just need to focus on the Mastering Chemistry homework. You need to focus on the Blackboard quizzes, and you also need to focus on studying for that last test, for that last week of school. Don't let it come around and bite you in the butt, because maybe, just maybe, you're one of those people that will have that 1 point between a D and an F. And if you let DNA come between you and walking across that stage, you are going to regret it. So, good luck with this portion of the lecture module. Good luck with all of the grades and the assignments that are out there that needs to be done. Hopefully, you will walk across that stage in a couple of days or a couple of weeks, and hopefully you'll have that diploma in hand so you can go out and work on DNA, and so you can go out and find that next new cure for cancer. And then you give me credit, because I want a cut of the pie. If it wasn't for me, you wouldn't have known it.